Prepare to be swept away into the mesmerizing tapestry of the cosmos as we unravel the captivating secrets of the galactic magnetic fields. Brace yourself for a mind-bending journey through the invisible forces that shape our galaxy, where celestial threads of magnetism weave an intricate dance amidst the stars. In this awe-inspiring exploration, we'll unlock the hidden powers that guide the cosmic ballet, unveiling a world where magnetic fields hold the key to understanding the mysteries of the universe itself. Get ready to embark on an electrifying voyage into the heart of the galactic magnetic fields, where science fiction meets scientific reality in a spectacle that will leave you in a state of electrifying wonder. Magnetic fields are a major agent in the interstellar medium, ISM, of spiral, barred, irregular, and dwarf galaxies. They contribute significantly to the total pressure, which balances the ISM against gravity. They may affect the gas flows in spiral arms, around bars, and in galaxy halos. Magnetic fields are essential for the onset of star formation as they enable the removal of angular momentum from the protostellar cloud during its collapse. MHD turbulence distributes energy from supernova explosions within the ISM. Magnetic reconnection is a possible heating source for the ISM and halo gas. Magnetic fields also control the density and distribution of cosmic rays in the ISM. What causes the magnetic field? The magnetic field of a galaxy is created in a similar way to how Earth's magnetic field is created, through the dynamo effect. The charged interstellar gas throughout the galaxy is moving through space as part of the galaxy's overall rotation. Whenever charged particles move, they create a magnetic field. The moving interstellar gas, therefore, creates a magnetic field. But this is not the end of the story. The magnetic field then acts back on the charged gas particles, influencing their motion in such a way as to amplify the magnetic field at the cost of the particles' kinetic energy. A complex, self-amplifying interplay of moving gas particles and magnetic fields results, which tends to form a long-term, stable, large-scale galactic magnetic pattern. The large-scale galactic magnetic field. The large-scale galactic magnetic field component has the following pattern. The magnetic field lines lie parallel to the plane of the galaxy and trace out giant azimuthal spirals emanating from the center of the galaxy. These spiraling magnetic field lines coincide with the spiral arms of the galaxy. Interestingly, these field lines point in different directions on different spiral arms, some pointing along the spiral arms toward the galactic center and others pointing along the spiral arms away from the galactic center. The galaxy's magnetic field is strongest in and near the plane of the galaxy, since that is where most of the matter exists. It gets weaker as you go away from the galactic plane. Why don't galaxies have a natural magnetic field like the Earth does? Each galaxy does have a natural magnetic field, but it is weak. The magnetic field of our galaxy is about 100 times weaker than the magnetic field of the Earth. The magnetic field of a galaxy has two basic components: a large-scale ordered pattern that mimics the shape of the galaxy, and a small-scale random pattern. The magnetic field component that has a random pattern is about 2 times stronger than the large-scale magnetic field component. As a result, you can only detect the ordered pattern of a galaxy's magnetic field if you make many measurements at different locations and average away the random pattern. If you were to place a space probe at some point in interstellar space and have it take a single measurement of the magnetic field, it would mostly be measuring the small-scale random aspect of the field. For this reason, such a measurement could not be used to determine the space probe's orientation or location in the galaxy. In other words, a magnetic compass in interstellar space would not point to some kind of galactic North Pole. On the other hand, if the space probe took many measurements at widely separated locations and averaged them, it could detect the large-scale pattern of the galactic magnetic field and use it for navigational purposes, assuming that the space probe already knew the large-scale pattern. The strongest magnetic fields. Neutron stars generate the strongest magnetic fields in the universe. However, the only way we have to measure their surface magnetic field directly is to observe the cyclotron absorption lines in their X-ray energy spectra. Recently, the InSight XMT team discovered a cyclotron absorption line with an energy of 146 keV in the neutron star X-ray binary Swift J0243.6 plus 6124, which translates to a surface magnetic field of more than 1.6 billion Tesla. After direct measurement of the strongest magnetic field in the universe at about 1 billion Tesla in 2020, the world records for the highest energy cyclotron absorption line and direct measurement of the strongest magnetic field in the universe have been smashed by a large margin. Probes finding magnetic fields. Space probes, such as the Voyager probes, have measured the magnetic fields of the planets, and even auroras have been photographed on other planets. The spacecraft Mariner 10 flew by Mercury in 1974 and surprised the science community. Mercury was thought to be cold and dead inside, thus having no magnetic field. However, Mariner measured a weak magnetic field, meaning Mercury must have some internal activity. Probes found that Mars and Venus do not have a significant magnetic field. Jupiter, Saturn, Uranus, and Neptune all have magnetic fields much stronger than that of the Earth. Jupiter is the champion, having the largest magnetic field. The mechanism that causes their magnetic fields is not fully understood. It is believed that in the case of Saturn and Jupiter, that their magnetic fields may be caused by hydrogen conducting electricity deep within the planet. Hydrogen near the planet's core may be compressed so densely by all the planetary layers above that it becomes an electrical conductor. The planet Uranus has an interesting magnetic field. Uranus' poles lie almost in the plane of its orbit around the Sun. The magnetic poles are fully 60 degrees away from the geographic poles, which results in a wild rotation of Uranus' magnetic field as the planet rotates. On the other hand, Saturn's magnetic field and rotation axis seem to be pretty much the same, making Saturn somewhat magnetically unique. As we conclude our exhilarating expedition into the depths of galactic magnetic fields, we are left in awe of the invisible forces that shape and guide the grand tapestry of the cosmos. These cosmic threads of magnetism weave through the vast expanse of space, orchestrating the dance of stars, galaxies, and interstellar matter. They hold the key to unraveling the enigmatic workings of the universe, from the formation of galaxies to the birth of stars. If you found our video informative, kindly subscribe to our channel so you won't miss out on our videos.